I need like extra like in centimeter. I don't know. It's alright. It's sponge. It's eraser. The large. Oh, did they actually steal it? I think they stole like. Did Huron have it? Like Huron has a like large sponge. No, but there's even one in the long math lab, but it's broken. It broke. I don't know. I don't want to use it. That's one thing. That's good. People are not interested in this. Like this, is like I also put it like I already put it very friendly in the like in the introduction. Like that's like everything though, like introduction of first course are not introduction to representation theory. Like, but also very friendly. Like I didn't prepare this for the first year, so that's kind of sad. That's all right. Is there any first years here? No. Okay. You're first year. You're first year. All right. Well,
Oh
it's
yeah,
like
you have people to indoctrinate now.
huh?
You have people to indoctrinate into this.
Right, right. How many people has habilitation instead? And so since how many people know what the ordinary categories are? Like just the definition. All right. Okay. So I shouldn't skip the first part. Okay. We can start now. All right. Thanks everyone for having me here. Gonna be a very friendly introduction to infinity categories. But yeah, we're gonna start with the ordinary categories, and we're not gonna spend too much time on it. And I'll define and try to motivate you guys about the infinity categories, which are nice things. Yeah. So for ordinary category, it has two things: objects and morphisms. Yeah, also notation, like if I write cursive, this means category, sometimes either ordinary or infinity. And when I write like C's and the D's, like these are like just objects. Yeah. And morphisms, they're like arrows between objects. This you can just consider like like a set of like points. Yeah. And morphisms are arrows between morphisms. It has a source and a target. And for these objects and morphisms to form a category, you need composition. So uh, A, B, C, D, E, R. Okay. So if you have two morphisms in this category C, you need to have all right. Key compose F must exist, and it sends C to E. Yeah, and you have associativity, which doesn't matter, right? So oh yeah, identity. Forgot. And for every C in C, the objects there exists the identity on C, such that since C to C, and when it composes with any morphism, it just gives you your own morphism. Yeah. Um. can give some examples. Some example that, for example, in high school, we all learned about a category of sets. The objects are just like sets. Morphisms are like functions. So yeah, so in my stats class, some prof used to say, oh, all maps are like functions, which is wrong. Like, yeah, and stats class. Okay, so yeah, I don't know. Like so like not all maps are like functions, right? What do you mean? Yeah, exactly. So like this like 1, 2, like you map to 2, 3, 4, right? For example. Like this mapping is not a function, right? It's a map, but not a function, right?
Depends on what you call it.
Huh?
I guess depends. There are a lot of people I assume it's map equals function.
Nope. This is a map, but not a function, obviously.
I call it a relation.
Relation. I've never heard that, but okay. Like it's just not, right? Like whatever. Yeah, so there's things called isomorphisms, which are invertible morphisms. I should give more examples. In linear algebra, we studied vector spaces over F, like F fixed field. This is a category. All vector spaces over F. The objects are just these vector spaces. Morphisms are like linear maps. If you have like random map or function, like usually it's not a, it's not a morphism. But they are, morphisms of sets, but not vector spaces. So yeah. So there is a difference. It depends on what categories you're talking about. And a bit more about isomorphisms. Isomorphisms in vector spaces are just isomorphisms, are just called like isomorphisms. Isomorphism in topological spaces are called homeomorphisms. So like,
Why don't you define as
it's just like, shoot. All right. Too many questions. All right. Um, Isomorphism in a category C is an invertible morphism. Yeah, what does this mean, right? Like a morphism, as we've seen, it's just an arrow, like the arrow, right? Source and target, and isomorphism is just like F, this F inverse, such that the F composed F inverse is identity C, right? Yeah, that's true, right? No,
that's not true.
that's not true.
It's on D.
First F inverse and
Ah, yeah, doesn't matter. Okay, it's just identity on this, and I guess sure, whatever. Like okay, just a matter of order, which don't matter at all, right? Okay, sure, whatever it is. Yeah, like the composed identity, this is an isomorph. So in sets, this is bidirections, bijective functions. In topological spaces, these are homeomorphisms.
topological spaces the form a category.
Yeah, I said that.
What's
Continuous functions. Thank you very much. Yeah. All right. I'm talking about groupoids. Groupoids. Groupoid. It is. It is a category. where the morphisms are isomorph. Where all morphisms are isomorph. I think this is evident enough. I can give some example. For example, equivalence relations on sets. Like the definition of equivalence relation is that xy implies like y x. I mean, let me be more precise, I guess. Equivalence relation sets. We should give objects and morphisms. What are the objects? Just like a set, right? Like some sets. Morphism? It's just some set, like some points, like
The objects are elements of some fixed set.
yeah, sure. Okay, just points. Like x, y, whatever. Like yeah, just points. Elements of some set. Morphism, if x is equivalent to y, then x to y. This is a morphism. Make sense? Yeah, and I claim this is a groupoid, which means that all morphisms are isomorphisms. Do you want me to show it or like? No, you don't want me to show it, or like okay, I will show the isomorphism part because like it's reflexive, right? Like y equivalent to x equivalent to y is saying that y is equivalent to x, right? So, right, and yeah.
You haven't shown why this is supposed to be a category at all.
It's transitive.
Identity?
It's by the definition of equivalence relation, right?
Yeah, but you never match.
Like, okay, the definition of equivalence relation has three parts: identity, transitive, and reflexive, right? Exactly. These three, each one corresponds to identity of categories, and corresponds to the composition. And the last one, reflexive, corresponds to the isomorphism property. Reflexive.
Reflexive is identity.
So like x, y is y, x.
Reflexivity is x is equivalent to x.
That's reflexive.
That's it.
Oh, okay, sure. All right, symmetric. Thank you. Yeah, I probably make like silly mistakes throughout, so please remind me. These are good things. Yeah. Which time do we have? 10 minutes. That's good. Welcome. Let's see. And I want to talk about universal properties and maybe commutativity of diagrams. Maybe functors. Should I talk about functors? Real time. All right. So what does it mean for something to have universal property? For example, G H F G minus kernel F. Like let's say just this is happen in the category of abelian groups. So this is a abelian group, and this is a abelian group. This is a homomorphism of abelian groups. And the category of abelian groups has objects as abelian groups and morphism as homomorphisms, right? So this is so we say first isomorphism theorem means that there's this universal property. What does this mean? It means for every homomorphism of a billion groups, like arbitrary ones, it factors through this object. Or people may say like this map. And this map is just like projection, like the quotient map. And they say we induce such a map, right? Yeah, that's right.
Different homomorphisms will have different kernels.
Yeah.
So what do you mean?
Factors
all-
through.
Yeah. How can they factor that?
Like they all have
They'll have different.
like if you fix a map, right? Like if you fix a map, there's a diagram and an object in this category that looks like this, that has these maps, right?
What do you mean? Looks like.
Like I want you to think combinatorially. Like maybe forget about the algebra, well, unless you're very good at it. Like you fix like in this category, like you're fixing a like 2 points and an arrow. So and this theorem suggests that there exists another point that look like this, and the triangle look like this, right?
That's the statement doesn't make sense. Why can't I mean we could just take this second
And it further states that what this object is, right? Like that's what this means.
does it?
Yes, this looks like G over kernel of F, right?
I think it's more like if you have a normal group, subgroup in it,
Yeah,
together as a projection map,
yeah.
then every morphism to anything that has kernel containing that group factor in.
Yeah, like I mean categorically doesn't that just means that like for any like these pairs and like there exists like diagram look like this? Like look like this and have and these like arrows are like this arrow is determined and this object is determined, right?
Determined. But
Like determined by the map in this category, right?
you could just take this third object to be G itself, and you could take
Yes,
Y to
but
be, then always you would be able to draw this triangle. So what's the point of this?
point is that we know what the point of that is that this object is this, and that like this lies in this category.
Maybe
Okay, I see what you're saying. Like
I don't see what the point of this construction is yet, but maybe you will expand on that.
okay. Okay, I mean, like this is supposed to be like some
Not the universe.
It's not.
This is what do you mean? Like sure, okay, like what do you call it? Like classically it means oh this composed with this, it's just that, and like oh always work, right? Like but what it means is that you, in this category you give like two objects morphism, and you can there exists another object in the same category such that these arrow compose like form a triangle like this, and they commute, right?
Where's the
That's not-
universal object? Can you point at a universal object here?
Not universe.
It's not universal. It depends on F. How can it be universal if
It's not even unique after unique.
This like that's just the difference. Like it just what depends on what the equivalence you're like thinking. Oh,
No, there's no equivalent. Say G is Z. I can take a morphism from Z to 0.
yeah,
Then the quotient by the kernel will be 0.
yeah.
I can take a morphism from Z to Z identity, and the
Yes,
kernel will be
yes,
0.
yeah, I know it.
So and the quotient will be Z. So they're completely different objects. How
Yeah.
can they be a universal object? If they're just
Like what I'm saying is there are like these sort of diagrams. Like the diagram makes sense, right?
Yeah.
Yeah, that's my point.
Okay.
Okay. Okay, I think we have some. Okay, I don't know. Are we using different definitions? I don't know.
Universal property.
Okay. Oh, that's not important. I don't think that's point.
You can mention universal property of product.
Like it's like combinatorically, it's initial somehow, right? Like that's what it is. Somehow initial. Yeah, that's exactly what it means. It's like as a limit. Whatever. Like this is getting like, I don't like this. Yeah. So I'll define what the group is. Group is a groupoid such that there is like only one object. Yeah. So a group looks like this, and yeah, this is what the group should. And one should understand these morphisms as like elements. Like this, for example, this is G, and there exists an inverse by the isomorphism such that G inverse is the identity, which is the identity element in the group. Yeah. So this is a short definition, but it is important if you want to. This gives you a very quick way to find the classifying space of a group. Yeah. And these are ordinary categories, and I'll talk about another category, and then we can move on to the higher things. Like this. This is really like right. I'll just say this. Like 0, 1, 2, up to n, such that there's a okay. Yeah. So the object of this this is called the linear ordered pairs. Absolute. Yeah, absolute. Yeah. So there's a morphism. The objects are just natural numbers, and if there's a morphism, if one is greater than the other. Yeah. And maybe we want to keep this category in mind, and we can move on as of the moment. Yeah. Over K categories. Like classically, these like K categories, for example, 2 categories. This is the so-called category of categories. There's a strict and a weak notion. I can define, which are give A, B, C, D objects, just like ordinary objects. And you have Tom, AB, Tom, AC, and theoretic. I define. Okay, I'll define. And CD. These Hom, well, it's a functor. It's a functor into sets usually, but in this case, it is a functor into categories. So these are functors from sorry, morphisms. That's all right. Morphisms in the category. categories. Okay.
This is secret.
Yeah, it is. Right. And, oh, yeah, it's supposed to be friendly for first years. Okay, I'll default. So okay. Yeah, I see why there are many people here. That's fair. Yeah. A functor between C and D, two categories. Uh, Maps objects. A B morphisms F into A B C C D E F E F E F G G G. Uh, uh, how to do this? Such that a functor between categories maps objects to objects and morphism to morphisms. For example, the forgetful functor from the vector spaces to the sets just forgets the vector space structures. Or we have span, which is the adjoint of that, and you give it a few numbers, and it gives you a vector space of the corresponding dimension. Depends on the how large your set is. And back to this. To define two categories. This set is a category, and such that it follows a associative property, well, composition. Sorry. Let this be. All right. Let this be X. Let this be. Oh, this won't work. All right, that's fine. I'll just write everything out like this. CD be enough space. AC CD AB BD AD. Yeah, so yeah, such that this diagram commute and the functors from this to this and this to this composed of this this to this and this to this. The composition of those two and the composition of these two as functors, if they are equal as functors, this is a strict two category. Yes.
Wait, did you say home AB is a one category?
It's a yeah, just a category.
So what are the morphisms?
Like it's a category of morphisms.
Okay.
Yeah, so the morphisms would be natural transformations.
Yeah.
Yeah, and yes, and then these are like functors. These are like functors, and yeah. If composition of those two and these two, like the blue ones and the white ones, are equal as functors, which this means this is a strict two category. But this is a bad notion because you're not supposed to ask for equality of functors. And that's why people introduced weak two categories, which means the functors are equivalent up to unique isomorphism, which is a bit better notion, but it's still like bad. And that's why we have like infinity categories, partially. Yeah, so questions about this actually? This might not be a good, yeah.
For the strict one, which one would be the same as?
The composition of this and this is same as this and this.
So
As functors, like they do map to the same object in there. If the composition of functors are equal, then the category is strict. The strict two categories, and this actually goes up by n. Like you can have n categories, but like you can see, like as you go up, like this goes bad, like this deteriorates like quickly. Like I don't think there's a like I think people once wrote out the definition of like a three category, and then nothing beyond that. Like it's just too much. Yeah. And we can get to the exciting part. Infinite categories should be you know, exciting. I mean, ordinary part is not.
is it acceptable?
Yes, it is very accessible. Like more than this. Like this is like nonsense.
Wait, so you said working with three categories is very hard.
No, like
Infinity categories.
anything not that's not the ordinary category is hard.
So
Like but the infinity is easier.
easy.
Yeah, infinity. But this infinity is not exactly the same as when you just number up the like it, but it actually generalizes any n. But it's easy.
Okay.
Yeah. Okay. So from now on, by space, I mean a like depends on who you are. This means that you can think as a nice space, like nice topological space. That's either like compactly generated, if you know what that means, or a CW complex, or or like like things with like circles, like yeah, like which are which is I hope that's easy, like just circles, like attached to each other, like different dimension, of course. Yeah, so let X be a space, and we considered this. What is this? See, on the top. Oh, yeah. I think I should say that, but like in the context of ordinary categories, I mean, as I drew, like, which some people don't like, but these categories are like triangles, and yeah, and in this case, like this generalized the idea of like them looking like triangles to like n simplices, because triangles are two simplex, yeah, okay, and this generalized the idea, like yeah. So given an x, if you take this map, this is the n simplex, which looks like x1 to xn plus 1, yeah, n plus 1, such that the sum of yeah. So in our sum.
Why is this squared?
Oh, you don't need the square?
Yeah,
You just need.
Oh, okay. Yeah, right. So that's
You need the coefficients to be non-negative.
just just these, right?
Yeah, so that it will be compact. Otherwise, it's just a hyperplane.
Oh, like this. Is this what you?
Is equal to one, but
Yeah.
each coefficient. Not like
What? Oh,
oh,
yeah. Okay. Like, okay. Don't worry about this. That's not. All right. Like, just these things, and like these things, like triangles. Like it doesn't matter. Like n-dimensional triangles, n-dimensional triangles. This is it's not. Oh, like n-dimensional triangles, n-simplicities. Like as a topological space.
we're describing his whole topic. It's just nonsense.
That's no nonsense at all. Like, oh, you see me through, and that's really hurting.
What's tall? What's tall?
Oh, like evaluate like continuous functions.
So this, okay. So this continuous maps from your n simplex onto X.
Yes. By Hom, like, by abstract nonsense, it's a functor going from whatever this thing you are evaluating to this category. But concretely, it's just the morphisms, continuous functions, and sending it to the, oh, sorry, I was wrong. Sending it to a set, just a set of continuous functions from distance, right? Like top means these as topological spaces. Yeah. Yeah, so I think I should first define it? Yeah, so this actually gives a simplicial set. What is a simplicial set? It is a functor. Yeah, simplicial set. Definition. It is a functor from an of contravariant to a set. Contravariant, you just flip the direction of the morphisms in here. This one, as we knew, like these are just like n linearly ordered pairs up to n, and evaluate this to set. And this is the simplicial set. Any functor, any contravariant functor is from this category to that category is a simplicial set.
This delta n has nothing to do with that delta n. Yeah.
Well, yeah, these are not the same. Like right now, as of the moment. But secretly, they are the same. Yes, secret for obvious reasons. Yeah. So ideally, this should make sense. Like this 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 gives a set of continuous functions which are called the n-simplices. These are I'm not sure if the
Isn't that just the like keychain group?
sorry, I don't know what that is. Like this should be the n-simplex. What do you mean?
I mean, when you have like n simplices, right? You can make the free abelian group
Ah,
on n
Okay.
simplices, right? And that's how you construct singular homology.
You don't have to.
yeah. Okay, I see what you mean. But
The same construction, of course.
it is the same construction, but you don't make it as a group. Like just as a set. Yeah.
So it defines set.
No, it is. Wait, what did I miss?
Your category delta n is just natural numbers with.
Yeah, linearly ordered pairs.
You're supposed to consider finite sets, finite ordered sets, where the morphisms are non-decreasing.
Ah, right. But wait, what is that? Oh yeah, is it not the same?
And there, of course, if you take,
Oh, you're saying, yeah, you're right.
there are much more.
Should be this, yeah, should be this, right? Like, because you want the things in between, like, and, uh, to work. Yeah. That's not so bad. Oh, God.
And you can,
Yeah.
it's not that, it shouldn't take that much time to find.
Yeah, true. I mean, like, yeah, this is not that good definition. It's not even correct. That's true. Yeah. Maybe I should erase this at the moment. I can do it in another way. Like, if we take this for granted, and this consider this as a category. No, you should not consider that as a category. But and okay, that's you should consider that as a category. That as a category. Then like for each n and m, these are functors which are non decreasing functions. It induces maps between thing n and thing contravariant of x of x. Yeah.
So you're
So
saying if we mapped one simplex to another simplex,
it induces maps between n simplexes.
by precomposition.
By yeah, that's true. Yeah, it's by precomposition. Yeah. Not sure if people got got this part. It's not so simple, I guess. I guess we can do a more like we can understand this more topologically. Which is much more simple, which is much simpler. You can have n to n minus one. These are the well, which don't really matter at the end of the day. Like you can always have both. Like these are the functions such that one and minus one. One and like consider all the functions that are like non-decreasing, right? What does that mean? When you evaluate this in here, you need to preserve the morphisms. Yeah, like so must be an injective function such that all of them line up and at the ith one it kind of goes down by one. That's non-decreasing. That's one non-decreasing function. Could be just the same
And if it's,
omit the last one. That's
if it's
that's
non-decreasing, you can just map everything to one element. That's
oh. So non-decreasing means strictly injective. That could be equal. You should include the because you want this. You want everything just identity. You want the inclusion.
yes, if you want inclusion, you need strictness.
Inclusion is not the strictly basic though. Yeah. Yeah. Okay. So like injective, non-decreasing.
That means strictly increase.
Is it?
Yes.
Oh, really? Okay, whatever. Injective, non-decreasing. Yeah. So this map should induce differentiation of the n simplex. Like for example, 0, 1, 2, right? This is, and it induces differentiation. If A is up, gives let's say gives I equals to 1, gives this. Yeah. So you oh no. 1 you get 0 and 2, which is line segment. Yeah. And if you consider the other way, this is from R delta n to delta n minus 1. This should be like integration. Yeah, I don't know if people use this summation as like the summation instead of differentiation, which is integration. Some people write that. Yeah, some people do. Some do that. Notre Dame does that. Basically, it says you have this and this and this. It gives you this as a two simplex. Questions, concerns? Abuse the notation a bit, but it's fine. Yeah, very fine. Are you satisfied? Are you convinced? And I think that's true. Oh, okay.
He's a supervisor.
Well, I hope he's not outside there. He'll be very disappointed. Yeah, okay, let's actually get to the point that you found what the infinity category is. Yeah. And infinity, oh yeah, and the simplicial set is just the colimit of synthesis, if that makes any sense. Yeah. And infinity category. So-called it has like a bunch of different names. Weak and complex. Quasi-category. Quasi-cat. What other names does it have? Like infinity 1, like infinity 1 cat. Like all these are like different names for infinity.
So there are infinity too.
Yes.
So are there infinity?
I sure. I don't know. I don't know. I can't answer that. I don't know. Like the idea is that if you study infinity 1, the rest should be like trivial, something like not trivial, but like this this should be the ideal generalization, basically. Why? Okay, let me define this, and we can talk about some sort of talk about it philosophically, I guess. Yeah, so is a simplicial set such that for every for S simplicial set S, but that extends to yeah. So what is this? What is this? These are the are the ice cores, which are the unions of every faces of the n-simplex, but the ith one, like everyone but the ith one. For example, this would be a horn, like 0, 1, 2. This would be horn, and if this is filled, then this is an infinity category. So this is very strong condition, and this is in the n equals to 2 case, I believe. Yeah, that's true. And yeah, I can give more examples if people want, but what do we think? We know what the horns are, and the horn filler is just this map. Yeah, if there are such things, then your category is an infinite category. And you want for all n and all I such this there are horn fillers. So why does this generalize categories like or higher categories? It's because in the ordinary category case, we have composition of morphisms, and we want to determine that uniquely. But in this case, it is determined up to homotopy, which is what we want. And one good example would be the fundamental groups. And we all work with fundamental groups, are important, blah, blah, blah. But fundamental groupoid is a better example because fundamental groupoids takes objects in the space and morphisms as just homotopy equivalence, like equivalence class, homotopy classes of path of the space. It determines the connected components, and the fundamental groups at each component. And what's a punchline? The punchline is that the punchline is that everything is isomorphism. Give me a second, please. Yeah, the punchline is that everything is determined after homotopy.
Can you show
how it's done?
what really what it has to do with something being determined?
Yeah, so we should, the reason why it's the infinite category is that we should consider the points, which are 0 simplices, as objects, and 1 simplices as morphisms. And the composition in the case as infinity category, the horn filler, gives not unique composition, but up to homotopy. In the case of fundamental groupoid, is they say that over this you have 2 points, right? You have 2 paths, F and G, and in the fundamental group case, this thing composes well. But in the fundamental groupoid case, it does not compose well because you do have this path, which is, let's call it H, by concatenation. For example, usually how people do it is that you define a new function such that this is running up at 2 times speed and this is running 2 times speed, so that you get a new path like this, and you take all the homotopy classes. But this is not unique because you can run this at like 3 times fast and this like not so fast, and you do get a different path. Like you get different functions, right? Because you're running on these 2 paths at different speeds. That gives you a different function. But the punchline is that these functions running at the different speeds, they are homotopy. So this generalizes the idea.
Saying the composition of these 2 paths should just be defined
After homotopy instead of like determined unique.
Yeah, but like the proper definition is that any map of a 2-dimensional triangle to the space such that 2 of its the edges map to F, G, And the third can map to any.
That's true. As long as it exists, then it's fine. Just more like the existence.
Yeah,
Instead of-
but we don't know which.
Yeah, and because like in the fundamental groupoid case, we've considered that like doesn't matter which concatenation you choose, they both of them should or any of them should be the desired composition. Whereas in the fundamental group case, it doesn't work. Right? And if you determine homotopy homotopically, then this should you get all the thing as in the same homotopy class, right? That's the idea.
Is this like an example of like the thing you drew there? Like you have 0, 1, 2, and then the
Yeah, sure. Yeah. I mean, like this path. Oh, that's this is a horn, but you can consider this as this path as a one simplex. You can map the one simplex to this.
And the idea with these horns was that you wanted the map that's like induced from 0 to 2 to be unique up to homotopy. So that I don't understand what's
More like if such thing exists, this is a two simplex. So like the whole thing, like the whole component would be a two like the whole connected component is this. Like you can't say that, like that's kind of the point, right? Like you can't say this path is this formula. It's everything and everything combined together as a two simplex. So all this. Yeah.
This particular path is a particular.
Oh yes, but
There are many possible fillers, but we don't know which. And third one.
no, all of them are the preferred one in the sense. Like you should not discriminate against any of them. Like
Yeah.
as long as they are.
Everybody is the preferred one. Nobody.
Well, yeah. Well, that's why we have like mod big class, right? Yeah. So we can talk about more fancy stuff if this is not enough. Yeah. So maybe I'll mention some application to like algebraic geometry, algebraic topology, whatsoever. There is this central notion called localizations. Yeah. The localization, the term originally come from localizing, let's say, for P of prime, we have the integer, and then we localize the way from P. We get that P1. This is sits inside of Q, and this is yeah. So this is called the localization at the prime P prime. Things here are just divided by prime added. This is ring, commutative ring, and this works for all commutative rings. Yeah, and can generalize this to infinite categories, and in particular, of course, topological spaces. What do? We choose some equivalences and set them to be the isomorphisms. In the topological case, we are choosing peak equivalences, which are multiple equivalences. But this means any map from fx to y. This induces isomorphisms of homotopy groups at any level, at any fundamental group and any higher homotopy groups. This is what it means to be a big equivalence in a topological category. And if we choose these as isomorphisms, then we get the homotopy category of the topological category, which is H of, which is expected. Like we can do this without infinity whatever. And this is of interest because, like, as I said, why do we use compactly generated spaces or CW complexes? It's because many spaces are not so well behaved, but homotopy theory, like, and homeomorphisms are such a strong notion that like homotopy equivalence does not like, and isomorphisms are just like the use is just too different. Like what one does not imply the other, right? Like homotopy equivalent does not imply like homeomorphism. That's why if we work in this category, homotopy theorists can do like much better things. And for algebra geometers, let's say, the category of consider an abelian category, let's say, and if you consider the equivalences as or you consider the chain category of chain complexes over the abelian category, and you take equivalences as quasi-isomorphism. Those are the ideal isomorphism in the category of chain complexes. And you localize that, you get a derived over A, which is yes.
So like by localizing categories, you mean like you're selecting like which morphisms to promote to isomorphism?
Which morphism you choose the morphisms to invert.
So it's like kind of analogous to like how you like everything outside of your prime ideal becomes like a unit. Right?
Yeah, so like how that's similar is that if you consider this, as I've demonstrated how you consider a group as a category, you consider this ring as like category. And for example, this is P, or like since away from P, these are not P torsions. And you are adding inverses. Like this is like the most simplest ones as choosing like equivalence. Your equivalence is like P torsion, and you are turning these elements, which are morphisms, when you view Z as a category, you are inverting them. So these morphisms, hence the P torsion elements are like isomorphic. Yeah. So yeah.
Can you
Yeah.
explain what's this, what localization has to do with infinity?
Oh, you can only localize infinity. Like you can only localize, like classically, you can only localize model categories, which are presentations of infinity categories.
And if we just given an alternate category and a collection of morphisms inside it, and we just
Oh yes, but this gives it more like a structure, like how this shows how like homotopy groups are like cohomology groups or homology groups. Like it's give a like a similar frame, because even though you're localizing the homotopy chain complexes over like an abelian category, right? You are still choosing homotopy equivalence. Like, but when you're localizing like chain, like category of chain complexes, you are choosing homotopy equivalence to be your weak equivalence. So yeah.
So what is so infinity about that? I can define quasi-isomorphisms in a purely
algebraic
without referring to any infinity structure.
I mean, this is just one application gives a framework. The point is that the real at least one of the motivation is that this is more general than the ordinary category, because in the ordinary case you ask unique composition, right? But where this is up to homotopy, which is a lot weaker than the unique composition, right?
I mean, but when you say composition is defined up to homotopy, you don't mean it's actually defined up to like this kind of homotopy, like a quasi-isomorphism. You're just being figurative.
I mean, but for any category, you can like consider it a homotopic, right? Like that's like any category can be turned into an infinity category by applying the nerve function. And you consider that as, and it has natural homotopy structures, and then I think that's how people work that, right?
What does it add to the localization structure, construction?
It adds to the localization.
Like that can be helpful if we want to consider derived categories. Or the H.
I mean, like it's more like a. You're saying this can be done without all the infinity, like BS.
Probably, but then maybe the structure gives us some additional problems.
Like it's just the same. It's just a homotopy equivalence that I think that's used.
So you would say that an infinity category has a well-defined notion of homotopy equivalence already embedded in it.
Let me see.
What's the connection?
That's model structure. The model structure gives this, and they are choosing some equivalences, which are that. I think that's true. Yeah, like you can take, like because homotopy groups, fundamental and anything higher, it's always has you can always take that of. Sorry, you can always take the. You can always consider the homotopy groups like the weak equivalences of infinite category. Yeah.
Oh, you're saying like if we have an infinity category.
You can always consider the homotopy groups, which are like yeah, like as a simplicial set, right? You can always consider the homotopy groups.
What does it have to do with?
I mean, like that gives you, doesn't that give you a BK equivalence? Like, but this your depends on what the model you choose. Like, it gives you a like morphisms of infinite categories, right? Like, gives you a BK equivalence. At least that's my.
There's multiple infinity categories now.
I mean, those are just notions. I don't know. I don't know what. I don't know what that means basically. I don't know what does like the statement there are multiple infinite categories. Oh, okay. Yeah. Yeah. Okay. It actually ended 2 minutes ago. And any questions? More applications? I don't know. Yes.
More applications and non-grading.
More applications. Oh yeah. I stole. We can steal Kai's thing. Like for example, K0, the K theory. We can build the infinity. We can build the K theory in the infinity setting. Quite easily. If we consider a vector bundle or a finite projective R module, and we take the singular simplicial complex that we take this functor to that category, and we that's a
What's category?
the category of let's say are finite projective modules. Or what?
Some function. Can you write down?
Okay, sure. All right. Take this. Oh, hold on. The finite projective R modules, and this gives you a monoid. You do a group. You do you take the you do a group completion, and this should give you this should give you a case series.
Thing of category is
Yeah.
just category.
Categorical, like like X. Where this is a category, and this is the category, the functors.
Then what is that?
Oh, this you take the you can you the isomorphism classes. Like you have category. Like if there's an isomorphism between the two, you replace that with one. The group completion. I mean, you give it a
The isomorphism. Wait, is this like a monoidal category?
this is a more I think that's well, if you want, you can give it like the how you just add give it the operation like how you add the modules.
That's what do you obtain? You obtain a group.
You like infinity group, like
This
like a
group,
case series. You got a case series as an infinity matrix.
it's A0 or
Case series of like
the ring.
sure, yeah. Yeah. Any other questions? Questions? All right. Okay.